Excellent. Okay, so the source of integration by parts. So integration by parts, another technique that's going to let us handle integration of certain functions like this one, and we'll talk about why that one's a good choice for integration by parts, but no other rule will help us solve or find that antiderivative. All right, so where does integration by parts come from? Just remember that every differentiation rule has a corresponding integration rule. For example, the substitution rule that we use comes from the chain rule, right? Where we're substituting in u, and we find u, or du is u, or sorry, f prime, well, whatever we set it equal to, and define dx, right? That substitution rule was derived from the chain rule. Well, there is a rule that corresponds with the product rule for differentiation. It's called the integration by parts. Okay, so now unlike the product rule, it doesn't give you a technique to integrate any kind of product. Just because you have a product of two functions doesn't mean we'll have a nice easy rule. But in certain cases, it will help us, and we'll walk through all those cases. So start with the product rule. dx of a function x, f of x, times a function g of x is what? What's the product rule tell us?
F times g prime plus b times f.
First times the second plus the second times the derivative of the first. Okay? So the derivative of fg is fg prime plus gf prime. Okay? Which would then correspond, this would be equivalent to an integration formula, right? Because if I know that the derivative of fg is this thing on the right-hand side, then the integral of the thing on the right-hand side is fg. The integral of f of x, g prime of x, plus g of x, f prime of x, dx, would equal f of x, g of x. That's just rewriting a differentiation statement as an integration statement. Those two statements are equivalent to each other. But this, I mean, while it could be useful, we could occasionally get lucky and have an integrand where we had a function times the derivative of a function plus the g of x times the derivative of f. I mean, if we just got lucky and that was the pattern that this thing was in, then we could use this rule. But rarely is that going to happen. What I mean by getting lucky is like, let's say the integral problem was the integral of, I don't know, x squared sine of x plus cosine of x times 2x dx. All right, stare at that for a second and notice that that looks like an f g prime plus g f prime. Right? What is your f in this case? Well, if I let that be f, right, and I let this be g, right, f is x squared and g is cosine of x. Actually, I need to make sure that that's negative. I'll put a negative right there. Then notice this right here is f times g prime, isn't it? X squared times the derivative of g, which is cosine. So the derivative of cosine is negative sine. And this down here is g f prime, isn't it? So I just got lucky that not only is it in the right form, but I even noticed that it's in the right form. That there is an f and g, so that, you know, this is now equal to x squared cosine of x plus c. The integral of negative x squared sine of x plus cosine of x times 2x happens to be x squared cosine of x. But you can see how rare that event would be, that you would get just the right chain rule. So you don't really have the product rule show up explicitly. But what you can do is, I'm going to take this part right here. I'm going to split it off as a separate integral. Since it's added together, I can do that. I'm going to move it to the other side. So I'm going to rearrange, and it's going to give me what's called the formula for the integration by parts. So what I end up with is the integral of f of x g prime of x dx is equal to f of x g of x minus the integral of g of x f prime of x dx, which is exactly what I have inside that box. That is the formula for integration by parts. Now, let's think about why that might be useful. I'm going to kind of dissect this right here. Notice on the left-hand side, in here, you've got two functions multiplied together, an f and a g, where the f doesn't have a derivative and the g does. And over on the right-hand side, you've got an integral where the derivative has moved. Right? Integration by parts essentially allows me to move a derivative from one part of the product to another. Okay? And the other one becomes the antiderivative. So let's come back to this one that I've got up here on the board, the integral of x e to the x. Consider integral of x e to the x dx. So here's the deal. If this right here, this x, was my f, then what would happen to it over here on the right-hand side? It becomes just a 1, right? And if this right here was my g prime, if g prime is e to the x, what is g? E to the x, right? So this right here is just e to the x. E to the x and a 1. So your integral going from x e to the x turns into a problem that only has an integral with e to the x times 1, which is an easy integral to do. You've stripped the x away from it by taking its derivative. Okay? That's what's going to happen with integration by parts, is you're going to take one integral and you're going to end up taking the derivative of part of it and the antiderivative of another part. Hopefully the antiderivative part is easy and the derivative part cancels out the thing that makes it hard to integrate. Okay? Now, I don't actually remember the formula in the form that's in that blue box. Okay? What I remember is what's down here at the bottom. In fact, I have this memorized so well that it rolls out of my head. I remember, I say it the same way every time I write it down. You want to practice saying this to yourself over and over and over again. The integral of u dv is uv minus integral v du. Okay, now let's see where that comes from. It's just the same thing. These two are exactly the same. All I'm doing is I'm letting u be f of x and v is g of x. Then du is f prime of x dx. And dv is g prime of x dx. Okay, so if I had integral f of x g prime of x dx equals f of x g of x minus integral g of x f prime of x dx. Let's fill in all the pieces. Right. That right there is u. This whole thing right here is dv. Right? So that's where we get u dv is the first part. It's f of x g prime of x. And then there's u there's v, there's v, all of this is du. So integral u dv is uv minus v, integral v du. Think. Integral u dv is uv minus integral v du. Say that 100 times to yourself between now and the homework assignment. Just keep saying it every time you write it down. Integral u dv is uv minus integral v du. That's integration by parts. Okay? You say that as often as you say the first times derivative of the second plus the second times derivative of the first. Or low d high minus high d low over low low, right? You've got all these little mnemonics in there. This one, just say that shortened version of that formula over and over to yourself again. But let's talk about how we actually use it, okay? So let's take this integral right here. Integral x sine of x. It's very much like the x e to the x, that I want to get rid of the x part because that's what makes this thing messy. There's no substitution that will work and get rid of that x. So what I will do is I will break this thing out and label part of it u and part of it dv. Okay? So your first step, label u and dv. Okay? Note the dx goes in the dv. So essentially, I have a few choices here. Don't write all of these down. We'll just, on this first one, write down the only one that's going to work. But you're going to find as you go through this, there's lots of ways to decide this. What I could do is I could let u be x and dv be sine of x dx. That's one choice. Right? Because now that integral is integral u dv. Right? It's integral of x sine of x dx. Integral u dv. You could also do u is sine of x and dv is x dx. That still makes the integral the same thing as integral u dv. Right? Because if you take sine of x times x dx, you've still got x sine of x dx. I mean, there's even a third and a fourth choice that are really bad in this case. You could let u be x sine of x and dv be just dx. Do you see what I'm saying? When you assign what's going to be u and what's going to be dv, you have lots of choices. By the end of this lecture, by the end of 7.1, I'll give you a little acronym to remember which order is probably the best choice, but really it's trial and error more than anything else. You could also do u is just 1, and then dv is x sine of x dx. All of those make the integral the same thing as integral u dv. Same thing as integral u dv. That integral sign turned into much more of an s than an integral sign. Okay. So lots of choices. Which one's going to be the right one? Well, generally, when you just have an algebraic expression like x times something, you know that taking the derivative of that x is going to get rid of it, right? So if you look at this formula up here, the one that's getting the derivative taken is the u, right? You're going to be doing du. So it makes sense in this case. I'm going to write down integral x sine of x dx. I'm going to let u be x. I'm going to let dv be sine of x dx. So what you're hoping for is that when you apply the formula, that the u term gets simpler or goes away, and the dv term is easy to integrate. Because now what I've got to know is, once I've decided on those, what is now du and what is v? So once you decide on u and dv, now you find du, and now you find v. Now if you know u is x, what's du? 1, nope, we're not integrating. We're deriving, taking a differential. Just like in substitution, if you let u equal something, take the derivative dx, right? So this would be 1 dx. Now to find v, that's where you go the other way. So to find du from u, we derived, differentiated, take the derivative. To find v from dv, we got to integrate. What is it? What's the integral of sine of x? Negative cosine. And we don't worry about the plus c yet, just for convention's sake, it'll show up at the end anyways in the final answer. Okay, so we decide on u, okay? Step 2 is to find du and v. Now we use the formula. The integral of u dv, is uv, so you take u times v. U is x, v is negative cosine of x, right? There's uv minus the integral of v du. V is here. So negative cosine of x. Du is right there. It's just dx. You with me so far? Okay. uv, I chose my u, I chose my dv, I then found du and v. Now I use the formula uv minus integral v du. And what has happened now is something very nice. We have negative x cosine of x. This minus and this minus will become a plus. Integral of cosine of x dx. The integral that was complicated and I could not integrate is now only dependent on an integral that I can integrate. What's the integral of cosine of x? Derivative of sine is cosine, so it's positive sine. And always remember your plus c. So this right here is the antiderivative of x sine of x. Left out my x up here, by the way.
So on the test where you ask specifically, like how that example says, use integration by parts?
Not always. There is a section in this chapter called basically which strategy to use. Okay, so I'm going to give you techniques, and you're going to have to decide which one's the best one to use for that. Okay, it's not always obvious, and it becomes more obvious the more of these that you do. Okay, I don't have an easy explanation as to when do I know to use integration by parts. Well, if everything else has failed, then you might try it. Give it a shot and see what happens. Okay. Then once you're trying it, you've got different choices. Should I use u as this part of the function and dv as this, or should I try something different? That's the pain of integration. There's no hard rule that works and handles all of them. Okay? You only learn by experience. Okay. So step 3 was to apply the formula. If you like steps, there you go. Again, the whole goal of that formula is so that the integral that you end up with on the right-hand side becomes simpler than the one you started with. If you come up with one that's more complicated and harder to integrate, you've probably gone the wrong direction and might try switching what's u and what's dv. Okay. Let's do another one. In fact, as you can tell from the homework or from the notes, it's just a whole bunch of examples. So let's keep doing some examples. Let's try the integral of the natural log of x. Now you may look at that and think, well, that's a nice simple one. I just looked that up on my table, but we've not done that so far. We don't have a function whose derivative ended up being log of x. We had the function whose integral was log of x. That is, we know that the derivative of log of x, is 1 over x. So the integral of 1 over x is log of x. But we've not ever done the integral of the log of x. We've not seen a function whose derivative gives me just log. Right? If you think long and hard about it, you'll recognize, even as simple as that looks, we've never done that. Okay? So, substitution wouldn't work. The only thing you could try substitution with would be log of x, but then whenever you take the derivative, you get a 1 over x that's not in there, so you don't have a way of getting rid of that. So, let's try this. Use integration by parts. So I need to let u be something and dv be something. I have basically two choices here. I can either put the log in the u or I can put the log in the dv. What makes the most sense? If you put it in the dv, then how are you going to find the v?
I'm thinking of the wrong one.
If you put it in the dv, you've got to integrate it, right? Which is the problem we're starting with.
I forgot which one.
But if you do it in the u, then you do the du, exactly. So you were wanting to derive it, but you're stuck in the wrong one. Okay. We want to take the derivative of it to get rid of it. So let's put it in the u, and then just make dv the dx. The dx always goes in the dv. Has to. Because it's a d. Just like dv, you've got to have a dx in there. Okay? So, now then, once step one, we've decided what we're going to do, let's now do du. And let's find v. What is du if u is log of x? The derivative of log of x, 1 over x. dx, thank you.
I was about to say plus c, but I knew that wasn't correct.
All right. Already told you no on that one once today. All right, if dv is just dx, by the way, that's like 1 dx, if that helps, right? What is the integral of 1? X. Okay, so here's what we've got now. The integral of u dv, that is log of x dx, is, what's the formula?
uv minus integral v.
uv minus integral v du. So uv is log of x times x. So I'm going to write that as x log of x minus integral of v, which is x, times 1 over x dx. There's dv. Oh, sorry, du. v du. v du. Integral of u dv is uv minus integral v du. Did we make our integral simpler? What's x times 1 over x? Can you find that integral? Minus x, and then plus c. So that nice little simple function log of x has an antiderivative of x log of x minus x. Okay? Just because I've got time in my schedule. All right, let's do another one. All right, so this is kind of like the one I started with when I was doing x e to the x. It's now t squared e to the t instead of just t e to the t. So let's try same approach, integration by parts. So let's do u and dv. What's a good choice for u and for dv?
Everybody should say u squared is u dt is dv.
Okay. Again, you could have tried e to the t over here. In fact, put your pencils down for just a second. I want you to at least see it in action. What happens if I do this? Okay. That's a valid choice, right? And I can even take the next steps pretty easily. Du would be e to the t dt, right? And v, I can integrate t squared. I get 1/3 t cubed. And so now when I do uv, I get 1/3 t cubed e to the t, that is this integral, is equal to minus the integral of 1/3 t cubed e to the t dt. Now that's a true statement. I mean, that is equal, okay? But have I made my life any simpler? In fact, I made it a little bit worse because now I've got a higher power, t cubed, right? So, if that happens in real life, and you notice that now your integral is a little bit more complicated instead of less complicated, then go back. Erase. And try a different approach. Let's go back now. Pick your pens back up. Let's try what your choice was, e to the t. Now, du is 2t dt, and v is e to the t. All right, so this becomes uv minus integral v du. Thinking that over and over again. uv would be t squared e to the t minus the integral of v du, so 2t e to the t dt. I just rearranged it, but it's still just e to the t times 2t. Okay? Is that simpler? It is, except it's not simple enough yet. Still got a t in there, right? So what are we going to do? Do it again, right? We made progress, tiny little step in the right direction. Let's take one more step further, okay? Let's do it one more time, okay? Do it again. Because if we do it one more time, the t will go away. We know that, right? Every time I take the derivative of a polynomial, it reduces by a degree. So anytime you've got a polynomial times something, you could always use integration by parts, as long as that something is easy to integrate. Okay? So I'm going to have now a new u. It doesn't matter what you do with this 2, by the way. That 2, you could pull it outside and then just do integral of t e to the t, or you can leave it inside with the u. I don't care what you do. Either one works. I think in my notes I pulled the 2 out, but we can leave it in there. Shouldn't matter. 2t. Just make sure you keep track of this minus sign that's out front here. Don't lose track of that, because it's going to now have to distribute across the integration by parts. dv would be e to the t dt. So now du is 2 dt. And v is just e to the t again. So here's what I've got. T squared e to the t minus, now I'm going to put it in brackets, uv 2t e to the t minus the integral of v e to the t du, which is a 2 and a dt. Now, you should be able to eyeball this one. What's the integral of 2e to the t? 2e to the t again. It's just itself. So here's what you got. Distribute the minus sign. I've got t squared e to the t minus 2t e to the t minus a minus makes plus 2e to the t plus c. That's now the function that if you were to take its derivative would give you t squared e to the t. So sometimes you'll have multiple applications of integration by parts. Okay? So as you see the algebra part of it, the algebraic part, the polynomial getting lower and lower degree, I could give you like a t to the 7th e to the t. You'd have to do integration by parts 7 times to get it all the way down to a constant times e to the t, right? But you just keep doing it, okay? There's another wrinkle that sometimes shows up, and this next example kind of walks us through that. Let's try this again. Instead of x sine of x, let's do e to the x sine of x. Kind of. It'll regenerate itself, but I can take advantage of that fact, and I'll show you exactly how. Okay? What's going to happen, and get a little bit of forethought up here on the front, it said that it's going to start repeating itself. Like if I use, for example, either the sine as du or even as just, sine as u or even in the dv, when you differentiate sine over and over again, right? It goes to sine, cosine, and then it comes back to sine, cosine, sine. It's going to keep repeating itself. And e to the x, whether you integrate or differentiate, it's going to keep repeating itself every single time. So unlike polynomials, which will eventually get rid of themselves when you keep deriving them, this one's going to repeat itself. So what am I going to do so that I eventually get rid of that integral that's hard to do? And I'll show you that there's a nice little trick to do that. I'm going to suggest u is e to the x and dv is sine of x dx. Actually, it doesn't matter, I don't think, in this case, which one you choose. It works exactly the same way, even if you get them backwards. So what's du? And v? Negative cosine of x. So that means we've got the integral of uv minus e to the x cosine of x minus the integral of a negative e to the x cosine of x dx. And I'm going to go ahead and just make that minus become a plus. Y'all see how that happened? Minus and minus becomes a plus. That's all. All right. And just like we did before, let's repeat that process one more time. Let's let u be e to the x, dv now be cosine of x dx. So that means du is e to the x dx, and v becomes just sine of x. So I have the integral. I have negative e to the x cosine of x plus uv, which is e to the x sine of x, minus the integral of e to the x sine of x dx. And just as we predicted, we're back where we started. If I keep going, it's just going to end up repeating itself over and over again, right? Now here's where I get creative. Notice this integral right here is equal to this, right? I'm going to write that out. The integral of e to the x sine of x dx is equal to negative e to the x cosine of x plus e to the x sine of x minus e to the x sine of x dx. All right? What are we trying to find? We want to know what the value of this thing right here is, right? If I had written, yeah, just move it to the other side. If I had written it like y equals this e to the x cosine of x plus e to the x sine of x minus y, and I said find y, what would you do? I'd just move that over there. I'd have 2y equals blah, 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 right? And then I'd divide by 2, and y is equal to 1/2. Da, da, da. I can do that just as well here. And have 2 integrals e to the x sine of x dx equals negative e to the x cosine of x plus e to the x sine of x, which then means divide the two across. The antiderivative I am looking for would be negative 1/2 e to the x cosine of x plus 1/2 e to the x sine of x. And now throw in the c for good measure, because I now have solved for that antiderivative without any integrals. So that's the beauty of something repeating itself, is you can take advantage of the fact and move it to the other side. Once the integral that you're trying to find shows up again in integration by parts, you can move it to the other side and solve for it. Not an uncommon technique. Okay? So far we've learned a few things about integration by parts. One, we've learned you have different choices for your u and dv that can make a difference. Sometimes you have to do a repeated application of it. Sometimes you have to do a repeated application and it still doesn't get simpler, but you can move one to the other side and solve for it. Okay, the last one I want to do is make sure you understand how we would handle this should we need to do a definite integral. Okay, in fact, I'll probably just have to finish this up. I'll either do it at 11 or I'll do it on Friday. But let me just point this out. If I have integral a to b of u dv, that's uv from a to b minus the integral from a to b of v du. So notice how the limits come into play, right? They apply to that first part of the function and then also to the other integral on the right-hand side, okay? All right, and we'll finish that page. Either do one example before we start the review, or I'll do it on Friday. I'll decide between now and then. All right, that homework, by the way, is assigned and ready for you to start working on. I think it's due Friday, but I'm gonna go ahead and move it to Monday so that you have a little bit of a breather after your test. Okay. See you in about an hour.